What's going on, Chem 20s? Mr. Walton here. Today we're going to do mole calculation, and then we're going to introduce stoichiometry. First, we're going to talk about mole calculations. This is just review. This first part is just going to be review from two previous units that you had. So we need the skill of calculating moles to be able to do kind of the next big thing. And the next big thing is stoichiometry. It's going to last a few days. It's going to last kind of about a week long, that kind of thing. And it's pretty important. It's one of the big rocks for this semester for Chemistry 20. So in order to start our mole review, what I need you to do is I need you to get out your data booklet. I also need you to get out your formula sheet, the one that you probably haven't used since the solutions unit. You probably used it a little bit in the gases unit. And then I need you to take out your calculator as well. So pause the video if you need a little bit of time to do that, but otherwise, we're going to go ahead and get started. This is 7.2, and it's a part of stoichiometry, but we're going to do mole review and stoichiometry. What I want you to focus on right now is some really important pieces of information in your data booklet and in your formula sheet. So get out your data booklet and go to one of the very first pages after the periodic table. So we're going to get out our data booklet and we're going to scroll past the periodic table to page 3, I believe. Nope, page 2. And on page 2, it's got a really good chart here. And this chart details a lot of different values and a lot of different things that we're going to be using over Chem 20 and Chem 30. And it defines them, defines their name, the symbols that we use in calculations, and it also defines the units. And I really want us to focus on the unit part of this as well. So what I want us to do is I want us to go down and I want us to find something about concentration. So we're going to go down and we're going to find amount concentration here. That's a really key one, amount concentration. And we're going to recognize that the unit for amount concentration is moles per liter. Now this is really important because whenever we're talking about aqueous solutions, we need this molar concentration to be able to help us figure out how many moles are in a substance or in a solution. And then we're going to go up a little bit and we're going to find something else that has moles in it. So just kind of scroll up in your data booklet and find something else that has moles in it. Okay, we're going to keep going. Of course, the amount of a substance, the chemical amount, is the moles of a substance. Sure, whatever. But then we see the molar mass. The molar mass is measured in grams per mole. So grams on top, moles on the bottom. And that's going to be really important in order for us to figure out the mass of a substance if we want the moles or the vice versa. Okay, that's good. And then later on in Chemistry 30, you'll talk about molar enthalpies in kilojoules per mole, and a couple other things. So those are really important pieces of information. We just got to define that. Molar mass is in grams per mole. Amount concentration is in moles per liter. Good. Now what I want you to do is I want you to take out your data sheet or your formula sheet. So it should look like this, Chemistry 20 formula sheet. You will be given a brand new copy of this on the final exam. And of course you use one of these on a lot of your unit exams. So I want us to look for moles in here somewhere. Same thing, I want you to go through this sheet and I want you to find moles. And it's pretty easy to find moles in a few different places. I'm just going to zoom in a little bit more. So the three places that I find moles are here. I don't know if you remember what that R value was called. And then here, and then here. This R value, I don't know if anybody mentioned it or mumbled it in class, but that's called the ideal gas constant. It's a constant that defines how ideal gases behave under certain conditions. And so it's got the units kilopascals, liters on top. So the way I like to write it, and I think the way most chemistry teachers like to write it, is 8.314 kilopascal liters over mole Kelvin. So 1 mole Kelvin. So that's really helpful for us. This is helpful because we get to convert between a bunch of different units in here. Now this is only for gases. We can only use these values if we're talking about gases instead of solutions or solids or anything like that. A couple other values in here that we can only use under very specific conditions. So VSTP means the molar volume under STP conditions, standard temperature and pressure. So I don't know if you remember, but I believe it's defined a little bit lower. Standard temperature and pressure is 0 degrees Celsius, 101.325 kilopascals. And then of course there's the other molar volume, which is SATP, which is 25 degrees Celsius and 100 kilopascals. So these two we can only use if we're using STP or SATP. But those are important values as well. So those are important values. I'm not really going to talk about these much, but I am going to talk about this. So kind of the big three things that I want you to focus on. The ideal gas constant has moles in it, so we can use it when we're converting units that involve moles. And then the other two are the molar mass and then the amount concentration. And that's what we're going to start with. We're going to define them, and we're going to define why they're useful. Okay, so the first thing I want to review is molar mass. Remember, molar mass you get from adding up all the different numbers and types of atoms in the formula for the substance. You should be fairly familiar with that, even though you might not have done it in a long time. So the molar mass is measured in grams per mole. What that means is that we can use this, the molar mass, anytime we want to convert between grams and moles. This value is helpful. If a question says, what's the mass, but it gives you moles, right? You can convert between moles and mass. That's the point of this. It's a unit conversion tool for us. So anytime we want to convert between grams, which is mass, and then moles, obviously is moles. Good, so that's going to be really helpful for us. The second thing we want to talk about is the molar concentration, or the amount concentration. Amount concentration is measured in moles per liter. So this thing is helpful anytime we have a solution, something dissolved in something else, and it allows us to convert between the volume of that solution and the number of moles of the thing dissolved in it. So this allows us to convert between the moles of a solute and the solution volume. Keep in mind the volume of the solution has to be measured in liters, right? A lot of the time it's more convenient to measure things in milliliters, but in our calculations they need to be in liters. Okay, no problem. And then the last one that we really want to talk about is the ideal gas constant. I don't care about the number right now. Obviously, I care about it when we're talking about the calculations, but I don't really care about the number. It's 8.314, sure, whatever. But it's important to understand that both liters and kilopascals are on top. Doesn't matter what order they're in. So I'm just going to, whatever order we want. Liters, kilopascals on top. And then on the bottom is mole Kelvin. And I'm putting a number 1 here just to show you that there are 8.314 liter kilopascals per every 1 mole Kelvin on here. And that'll be important a little bit later on when we do our calculations. I'm sure you're a little bit aware of that. So now why is this important? It's important because for any gas, this allows us to be able to convert between the volume, the pressure, the amount, and the temperature. If we want to figure out what pressure will something be if we're given the volume, the chemical amount, and the temperature, then we can do that. We can use that using this value. So this allows us to convert between pressure, temperature, moles, and volume of a gas. Now, I know it's a little bit annoying going through this again because a lot of you already know that, and it might seem like a waste of time, but it's really important that we understand that every single one of these values is a unit conversion tool. So grams per mole converts between grams and moles. Moles per liter converts between moles and liters. Liter kilopascal per mole Kelvin allows us to convert between any one of these units for a gas. So what we're going to do next is we're going to apply these skills in a few examples, and then I'm going to get you to test yourselves and prove to yourselves that you know how to use these. And then in the second half of class, we're going to move on to something else that requires some of this skill or some of these skills. Okay, so example number 1. How many moles are in 3.50 grams of calcium nitrate? So how many moles are in 3.50 grams of calcium nitrate? Give you a second to write that down. But the first thing that we should be thinking to ourselves, and feel free to pause the video at any time if you need to, the first thing that we should be thinking to ourselves is, okay, it wants moles and it's giving us grams. So we need to be able to convert from one unit to another, and there's kind of 3 different ways to do that. There's the molar mass, the amount concentration, and the ideal gas constant. Well, it didn't give us anything about gases, didn't say anything about liters, kilopascals, or pressure, or anything like that. It didn't give us anything about moles per liter because it's not dissolved in water. It's not a solution. The only thing that we have available is grams and moles, right? So we're going to use the molar mass. Now, one of the difficult parts with using the molar mass is for us to be able to calculate the molar mass. In order to calculate the molar mass, you need your periodic table, and you need to be able to identify what the formula for this substance is. So, another reason why we reviewed this a little bit earlier is because calcium nitrate is an ionic compound, metal, non-metal. So we got to figure out the formula. Calcium is 2+. When you look at your data booklet, and when we talked about yesterday, nitrates being 1-, we need 2 nitrates and 1 calcium. So the formula for it is calcium nitrate. 2 nitrates for every 1 calcium. Pause the video and then go ahead and do the molar mass calculation for this. Actually do it on your calculator. Take out your data booklet, look at the periodic table, do the calculation. Prove to yourself that you can do the molar mass calculation for this. Give you a couple seconds, pause the video, and then I'm going to go ahead and shout it out. Okay, the molar mass for this thing, when you add up 1 calcium, 2 nitrogens, and 2 times 3 is 6 oxygens. 1 calcium, 2 nitrogens, 6 oxygens should be 164.10 grams per mole. Okay, that's helpful. This allows us to be able to convert between grams and moles. So when we're doing unit analysis, this might be a little bit of a blast from the past, but when we're doing unit analysis, one of the most important things is that we tell ourselves and tell everybody else, what unit are we looking for? It says how many moles. Sure, no problem. So we're going to tell ourselves we want moles. So we have to start with moles on top. By default, any unit by itself, right, is on the top of a fraction. So moles out of 1. That's how any single unit is. So we need moles on the top. I don't see anything in moles in the question, but I see moles in our molar mass. So you go 1 mole. We're flipping our molar mass over 164.10 grams. So that's great. I'm going to really baby us on unit analysis, and we're going to go slow, and it might be painful at first, but I think it's going to help and pay off after a little bit. We're looking for moles, and we got moles on top. That's fantastic. Now our job is to cancel out any other unit that we don't want. We don't want any other unit than moles, so we got to cancel out mass. The way we're going to cancel out mass is by putting mass, grams, on the top of the next fraction. We see that in the question they gave us 3.50 grams. And I can write that over 1. So when I do this calculation, I'm going to get a little bit of an awkward number. You double check that that's what you get. So on our calculator, we're going to go 1 times 3.5. We don't care about the 1. So we're just going to go 3.5 divided by 164.10. And we should get 0.0213284 moles. Now, if we weren't done the question, we would keep all of those digits. If we are done the question, like we are right now, then we'll round to 3 significant digits. That's how many was given in our original question. 0.0213 moles. Okay, hopefully that wasn't too painful. Hopefully that was a little bit helpful. We're going to go through a couple more examples here. So the next example that we're going to do, example number 2. How many moles of acid are in 300 milliliters if it has a concentration? So hopefully you remember square brackets means concentration of 0.745 moles per liter. I'll give you a second to write that down. Feel free to pause the video if you need to. How many moles of acid are in 300 milliliters if it has a concentration of 0.745 moles per liter? Okay, So we want moles, and they give us volume. They're giving us moles and milliliters. Well, they're also giving us moles per liter. Remember that molar concentration allows us to convert between moles and liters for a given solution. So this is going to be helpful for us. We're going to take this, and that's going to be one of our most important pieces here. So we're looking for moles. Tell yourself that you're looking for moles. We need to start with something that has moles on top. I'm going to start with this molar concentration, 0.745 moles per 1 liter. So this is good. By telling ourselves that we want moles, that means we need to get rid of every other unit. How do we cancel liters? We got to cancel liters with liters. The problem is I see 300 milliliters. So what you have to do is you have to convert 300 milliliters to liters. Do this in whatever way you want to do it. Convert it in the actual unit analysis section if you want. I've always done it as an aside. So 300 milliliters divide by 1,000 is going to be 0.3 liters. So I'm going to multiply by 0.3 liters. This allows us to cancel liters and liters, and we're left with moles. That's what we wanted. That's the reason why we told ourselves we wanted that. So when we do this, put 0.745 times 0.3 into your calculator. You should be double checking these calculations with me. I've been known to make mistakes. You better be watching me. So when we do this, we're going to get 0.2235 moles. If we're not done the question, it's okay to take all of these digits. If we are done the question, then we have to round to 3 significant digits, 3 digits, 3 digits. So we would round to 0.224 moles. Perfect. So hopefully this is helping, kind of a little bit of a blast from the past. I totally get it. It's understandable if it's kind of a little slow for some people. Example number 3. So how many moles of hydrogen gas will occupy 10.0 liters at a pressure of 150 kilopascals and a temperature of 45 degrees Celsius. Woo! How many moles of hydrogen gas will occupy 10 liters at a pressure of 150 kilopascals and a temperature of 45 degrees Celsius? Nice! Okay, all right. Well, what we got to ask ourselves is which unit conversion tool do we need? There is only so many unit conversion tools, so hopefully you've had a chance to write this down. I'm going to go back here for a second. We ask ourselves, okay, do we need the molar mass of this thing? Well, molar mass converts between moles and grams. It's asking about moles, so that's great, but at no time does it give us the mass. So we don't need the molar mass in this particular case. So that's not going to be helpful. The amount concentration, that's only for solutions, something dissolved in something else. So an amount concentration isn't going to help us. It sounds like this is pure hydrogen gas. The ideal gas constant. So we're talking about a gas, check, and it gives us the volume, the pressure, and the temperature, and it's wanting moles. So this is really helpful. We're going to need the ideal gas constant. So let's go ahead and just kind of write that out. The ideal gas constant is 8.314 liter kilopascals over 1 mole Kelvin. Let's think about this for a second. It's asking us for moles, so when we do our unit analysis, we got to tell ourselves we want moles. Can we cancel everything out? We want moles, that means we need liters. We have liters, check. We need kilopascals, we have kilopascals, check. And we need Kelvin. Do we have Kelvin? Nope, we don't have Kelvin. I don't know if you remember how to convert between degrees Celsius and Kelvin, but you're either adding or taking away 273. When we go from Celsius to Kelvin, we're adding 273. Remember, you can't have a negative temperature in the Kelvin scale. You can't have a negative Kelvin. So when you're converting to Kelvin, you always add. You never take away. Okay, so 45 degrees Celsius plus 273 is going to be 318 Kelvin. Now we have kilopascals, liters, and Kelvin. Now we can do our unit analysis. So we tell ourselves that we want moles. So we got to start with moles on top, right? Whatever unit you're looking for is by default on top. So we need to flip the ideal gas constant. 1 mole Kelvin over 8.314 liter kilopascals. This is awesome. We want moles, so we got moles. So we are kind of close to being done. We just got to get rid of some values. That's all we have to do. So let's start getting rid of units one by one by one. Miss Newton might do this a different way, but this is the way I do it. So I want to get rid of liters and kilopascals. They're both on the bottom, so I'm going to put them on top. I need something with liters in it, and it says 10 liters, so I'm going to put 10.0 liters over 1. That's the way I do it. Miss Newton might do it a different way. That's fine. So liters and liters cancel. We got to cancel out kilopascals, so I need 150 kilopascals over 1. Doing that is going to cancel out kilopascals and kilopascals. And finally, I need Kelvin on the bottom to cancel it out on the top. So 318 Kelvin. So Kelvin and Kelvin cancel, and I'm left with moles. Once you have the unit that you want, and once you've gotten rid of all the other units, stop. You're done. You don't need to do anything else. So, when we're doing our calculation, this is the one that I did want to show you on the calculator. So we're going to multiply all of the tops and divide by all the bottoms. That's the way I would do this. So I would go 10, that's the only number on top so far, times 150. Those are the only numbers that I care about on top. Divided by, because we're dividing by two numbers that aren't one, we got to use brackets. So 8.314 times 318. 318. And I'm going to get 0.567 blah, 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 and we're going to round 0.567. I don't know if this mole review was helpful. I don't think it was helpful for everybody, but I think it was helpful for some people. So thank you for allowing me to do this, even though you had no choice. That's okay. So what I want you to do now is I want you to take about 10 to 15 minutes to try out a series of 6 questions. There's 6 practice questions that I want you to do. And then after that, after a little while, we're going to go over an introduction to stoichiometry, and we'll talk about what that is. Just a big fancy word. We'll talk about what stoichiometry is in a little bit. Okay, so have fun.